so let me do this question. This is again one of the projectile motion questions and part of the large number of new questions I've put in that I'm trying to kind of get done so that I can once again say I've done all the homework questions. Look at those homework help videos. Now this looks like it has more parts than usual, so let me read carefully. It says when a field goal kicker kicks a football as hard as he can it's giving me some angle information, so let me start by writing those down so I don't forget that I have that information. Theta equal to 45 degrees. The ball just clears a 3-meter high crossbar, so I'll say the height that it reaches is gonna be 3 meter. That's really what I care about. And I'm given the distance of a goalpost at some distance 42. I'm gonna give these symbols height h and the range r, which will be 42.6 meters away. Okay, what is the maximum speed the kicker can impart to the ball? Okay. I guess that can make sense. I want to replace the must, but I guess you're describing what has already happened, and the can makes sense because kicker has already done it once, so we know it's within the kicker's capability. Okay, so what is the maximum speed? So this is almost a standard projectile motion question. You could oh, you know what? But one thing that makes it slightly challenging is that we're not talking about. So actually, let me not label this R because this is not what we would call range. So I should really call this maybe D, distance D. If it's landing back on the ground, then that would be like standard setup. There are derived formulas for range in your textbook and all that. But trying to figure it out to this height means I need to do the kind of do the projectile motion analysis from scratch. So when you are doing that, so you start out by defining the axis. So in almost all the projectile motion questions, you will want to define x to be horizontal, y to be vertical, and that's really because there's gravitational acceleration that's downward at minus g. So with that in mind, really the main thing that I need to do is I need to oh, this is not maximum speed. That really should be the minimum speed because he might be able to do more. He can at least do it. But let me not nitpick the wording of the question. So let me label this speed V naught. That's the initial speed that the kicker imparted to the ball. And if I'm representing that initial velocity vector in two-dimensional space, I need to break it up into two components. I need to break it up into x component and the y component. And we are helped by the fact that we are given this angle, 45 degrees. I'm gonna just treat it as known and just deal with the things symbolically until I need to plug in numbers. So when you are dealing with the projectile motion, that's one of the first things you will have to do. Break up your motion into x and y component, and often it involves breaking up velocity vector components. Once you have done that, then you can write down projectile motion equations. There's one for the x direction, x component, and the equation that I think is usually helpful is the one that deals with the I guess the position. The velocity one is too simple. It's basically going to be your initial velocity, same throughout because no horizontal acceleration. So when you are looking at the distance, the x position as a function of time, let me call it x final, and I'll label my time as time final. My x final is going to be equal to usually most generally there's an x initial position, but let me just set this to 0 by setting my coordinate axis so that I can say this where it's starting is x equal to 0. So 0 plus, now there's a displacement due to the initial velocity, that's gonna be v naught x times the t final for the final position. And because no acceleration with the x component of motion, there's no displacement due to acceleration. And we are done. The y component of the motion, depending on the context, sometimes the equation dealing with the final velocity is helpful. Let me just write it down. I don't think it'll be helpful for part A, but let me just write it down. You can say the final y component of velocity is equal to the initial y component of the velocity, and then there's change of velocity due to the acceleration. Let me use the fact that it's downward at g, so it's minus g times the final time. Sometimes this is useful. I don't think right now, no. Like if you're trying to figure out when the projectile reaches the top, that's where you have information about the final y velocity. It's gonna be 0 when it's at the top. So sometimes that scenario can be useful. But I think what will be more useful here is the vertical version of the position expression. The y final position is equal to initial y. Again, I'm gonna set my coordinate axis so that I don't have to deal with the extraneous constant, plus the displacement that you can attribute to your initial velocity, v naught y t final, and then there's kind of adjustment to your displacement that's due to the acceleration. For gravitational acceleration, it's going to look like minus 1/2 g t final squared. I did a derivation of this kinematics formulas in another lecture. So with those, this is the check I like to do. So I'm acknowledging one equation I probably won't use. So let me cross it out. I have two equations. I would like to make sure I only have two unknowns, because that's kind of the basic solving system of equations. So x final, that's going to be my d. I'm given that, so I know that. My initial x velocity, I don't know it, so that's one that I don't know. T final, I'm not given that, so I don't know. And y final, that's what I labeled as h, I know that. My initial y velocity, I don't know, and I haven't counted it yet, so I'm counting it. Oh, third unknown. T final, I already counted it, I don't have to count it again. So I have three unknowns and two equations, and that's mainly because I guess there's two ways to deal with it. These v naught x and v naught y that I counted as separately unknowns, it's not really the case because I know the theta. I know theta is 45 degrees. So I really have only one unknown, v naught. So I could express these two in terms of their trig functions, using so and ka. V naught y would be v naught sine theta. V naught x would be v naught cosine theta. And you can plug those in, then now you properly have only one unknown. Let me take a different tack. So what you can do is, I guess you can just, this is a more kind of maybe systematic way to do it, one that makes sense if you are programming things in. So let me do it set up the system this way, and I'll use a SageMath to solve through this. So instead of plugging this in like a normal person, I'm going to write down additional equations with additional unknowns. This is how information is expressed when you are doing physics problem solving. So the information that I know about my v naught y, it's expressed as another equation. I guess I can just use this. So that's an equation. That's my equation number 3. And in writing equation number 3, I introduce another unknown, v naught y. And v naught x is, sorry, that's not another unknown. I already counted it here. So v naught is another unknown I introduce. So up to now, I have 3 equations, 4 unknowns. But the next equation, one that relates v naught x to v naught and cosine theta, that's my 4th equation. And now I finally haven't introduced any new unknowns. So I have 4 equations, 4 unknowns. It's solvable. Now I'm doing this more formal way than it needs to be, and I'm in some sense taking longer time, but let me save some time by letting SageMath do it. And this time, because SageMath doesn't have to solve for any angular values, it'll work fine. SageMath is really good at solving kind of linear system of equations, and not so good at inverting trig functions. So you have separate tutorial videos of me showing this SageMath in more detail. So let me just do a quicker version of this here. I'm going to define all the variables I'm using. So vars. Let me do some simple substitutions that I know I'm gonna end up doing. This x final, that's my d. This y final, that's my h. I have values there, I'm going to be using it. So my variables are going to be d, v naught x, that's one of my unknowns, t final, that's one of my intermediate unknowns, and h, and v naught y, another one of my unknowns. I already defined t final, I need a g, and then I need a v naught, and I need a theta. If I forgot anything, it'll complain. And I need to define my equations. Let me define equation 1 as written. D is equal to, and there's a distinction between, this is an assignment symbol. It assigns what's on the right hand side into this variable. And this double equal sign is the one that says the logical equivalency. That what's on the left hand side is equal to, equivalent to what I'm going to be writing now. V naught x plus times t final. Equation 2 is h is equal to v naught y times t final minus 1/2 times g times t final squared. And equation 3 is equal to v naught, that's these two equations that I defined to express the knowledge about v naught. So v naught y is equal to v naught times cosine theta. Oh, sorry, sine theta. And the sine function, SageMath knows it, it's defined internally. V naught x is the v naught times cosine theta. So with these 4 equations defined, to solve it, I say solve. And then the list of these equations, equation 1, 2, 3, and 4. And give it the 4 unknowns it's solving for. And the rest of the symbols, my computer algebra system will treat that as known. So the 4 unknowns are, let me list them in the order I care about them. I really care about the v naught. That's the quantity I need to put into A. And I need, as an intermediate quantity, I need v naught x, which I don't really care about. V naught y, which I also don't care about. T final, which I also I don't care about. So yeah, let's see what it gives me. I'm gonna click evaluate. It'll either complain about something. I mix that. It's probably var. I keep mixing up between var and vars. Yeah, wait. Solve complaints. Cosine theta is not. Oh, I made that big boo-boo. Okay, double equal sign for actual expression of logical equivalency, numerical equivalency. All right, I did everything. Now it's giving me 2 solutions. It looks like it's giving me a negative solution and a positive solution. So let me just pick out this one. So this is how I'm gonna be able to pick out just that solution. SageMath, out of the solve function, it gives me the solution in like a list of lists. So this is inner list here. That's the second element of the outer list. So after solving, I'm looking at the second element. It's 0-based index, so 1 is the second element. And that'll give me this entire set of solutions. I just want the first one. That's my v naught. So that should just give me the v naught, the second solution. That's hopefully positive. So let me plug in all the numbers here. This is a kind of SageMath expression. It's got a bound method that lets me substitute in values. So I'm gonna substitute in the values I know. D is equal to 42.6. G is equal to 9.8. Just everything in basic SI units. H is equal to 3. And theta, I have to be careful. SageMath only understands radians, so I have to convert 45 degrees to radians. To, I guess that's pi divided by 180. Let me see what kind of calculation it does. If it does an exact calculation, I'll try to force it to do a numerical approximation. Let me substitute these in and see what's left. Good, yeah, it's trying to do this exact calculation, which is annoying. I can't just plug this in there. So let me put in on the lowercase n is a built-in function that makes SageMath do kind of numerical approximation. So this is what I'm substituting in. Then it'll give me something. 20 something. Wait. That's not doing that. Let me see. So instead of pi, let me do 3.14. It's gonna be close enough. The- what? Why is it? That is so annoying. So if I just don't plug in theta, what will it give me? Oh, I see. That's square root of that's popping up even before. Um, so I don't think there's an easy way for me to get rid of that. So I guess I'll have to do it this way. So let me put in theta. 45 times pi divided by 180 is fine. And so sometimes, when you're dealing with these kind of more persistent exact expressions, now you can't simply put this entire thing through numerical approximation. It'll error out because V naught is it's a symbol. You can put symbols through numerical approximation. So what you have to do is out of this expression for an equation, you have to basically take the right hand side, which has that numerical portion. So I'm going to take the right hand side of the expression, and then that can be put in through the numerical approximation. So doing that will give me 20 something, 21.19. And one of the reasons I did this, maybe I could have done, let me do this. I'm going to put this in, submit, and then see if I actually could have done what I just assumed I couldn't do. It's possible I could have actually just put in the exact expression. Yeah, I mean, it's a little bit I don't think that's the normal thing to do, but let me just try it. 29.97 times, because I have access to this square root, 1 over 2. If the system lets me do, then why not? Yeah, okay, all right. You could do that. That's kind of an unusual answer, but sure, why not? So one of the reasons I did the SageMath is I figured maybe I should have read ahead, but I didn't read ahead. But I figured this whole setup would help me solve the remainder of the question quickly. Let's read. In addition to clearing the crossbar, the football must be high enough in the air early during its flight to clear the reach of the onrushing defense lineman. The lineman is 4.6 meters away. That's the vertical reach of that. Can he block the 42.6 that field goal attempt? Okay, so it's asking this question. So the trajectory of the ball is already set. So it's the question of I think so one thing that I think I don't want to do is trying to plug in both of these numbers. What I think I should do instead, I should try to figure out where will the ball be. So imagine imagine the ball has traveled for a small d distance of 4.6 meters away, and at that point I want to figure out what is the height, small h, and I can compare this number to 2.5 meters to figure out could the lineman have blocked. So going back to my equations, I think that changes some things. So before my height h was known, now it's not. So for the purpose of the SageMath code, I'm going to use the same capital D and capital H. But for D, what I'll do is I'm gonna say my D is 4.6 instead of 42.6. And my H will not be specified anymore. And instead, I think I know. I guess let me do it this way. So V not so. I think that'll. Let me just V not so. Let me make sure that all works the way it's supposed to. Yeah, I have a solution for V naught, and that'll be part of the substitution thing I'll be doing, because I need to treat V naught as a known quantity, and I'm really doing a new kind of solution with different unknowns. But the equations themselves don't really change because this is the kind of the projectile motion equation. This is also projectile motion equation. The structure of the equation doesn't change. What changes is instead of treating these series of v naught quantities as unknown, what you are saying is now I think so v naught itself will be known, but I think I need to treat these as unknown so that the equations 3 and 4 still make sense. And I will say I don't know h. That's what I'm now trying to solve for, and that's the first answer I'll get. So let me just put this into my buffer. So when I do this solve, then it'll give me the solution for h out of here. Yeah, in terms of all the things I know, and I can substitute in all the quantities. Again, this is still, I don't know if I want the, I think based on that, I get only one set of solutions. So I want the first element now, and the first element still. And I don't want to plug in a value for h since I'm solving for it. I do want to change d to 4.6. Everything else I think is the same. Now when I do it this way, there will be a one unknown still. V naught will still be an unknown. So I need to plug in a V naught, and I can do that through this here. The substitute syntax, it accepts a few different formats. One of the formats it accepts is like an equation. So this is a variable containing that equation. I can pass it as a kind of input to substitute, and it'll substitute in the value of V naught, I think. And it gives me this height, 4.138. Now I can compare it to the height of the vertical reach of the lineman and report the height. Oh, that is what it's asking. Okay, so 4.138. Yeah, I thought I was clever doing what I was doing, but that's what the question is actually asking. Yeah, so comparing this, now you can say, oh yeah, the lineman cannot catch it. So what if the lineman were 1 meter away? Yeah, so this is the reason I set all this up. It's a lot easier in the computer algebra system to change the numbers, kind of try alternate scenarios. This is now 1. I don't think I have to change anything. Then the height of the football at the location is now 0. So if lineman is that close, then they will be able to now intercept the ball. Yeah. So yeah, I guess don't know if it's necessarily all that much harder. The final height being at a different height than the starting height, it does make the algebra slightly harder. But I think I kind of swept a lot of that under the rug by using computer algebra system, which you can. The only thing to watch out for is if you ever have to like solve for the angles themselves. SageMath isn't so good at dealing with the trig functions when it has to invert the trig function. So you kind of want to watch out for that.